So good afternoon, everybody. My name is Ivanova from the University of Manchester, and today I'm going to present to you research titled Automated Selection of Free-Floating Planet Candidates from Kepler K2C9, which is part of a PhD project supervised by Dr. Eamon Kerens. Obviously, there have been quite a few talks before me, and I'm stating the obvious here, but just for completeness, gravitational microlensing provides a unique method to detect intrinsically faint and distant objects that are otherwise challenging to detect, such as free-floating planets. As we discover more and more, we see that free-floating planets exhibit a variety of planetary masses, and to date, gravitational microlensing is the only method that is capable of exploring this entire population down to Mars mass objects. Generally regarded as elusive, not only because we're still not certain on their formation mechanism, but also, and this is the question that we focus on, unbound planet studies are incomplete, and estimates of the distributions are widely varying. For Jupiter mass free-floating exoplanets, for example, we see estimates as reported as a quarter as common as sequence stars, as reported by Mroz et al. 2017, to them being twice as common as galactic stars, such as the estimates from Sumi et al. 2019. And this is the gap in knowledge we wish to fill here, is this parameter space occupied by free-floating planets, which is said to be fully explored, and we wish to do that by conducting a fully automated analysis of the K2C9 data to use together with simulated data with the goal of recovering Kepler's efficiency of detecting free-floating planets, ultimately aiding our understanding of the galactic abundance of free-floating planets as function of mass. The data that we wish to use is data from the second light of Kepler, which is a mission that officially began in 2014 as an extension of the Kepler mission. So after two of Kepler's reaction wheels broke, the Kepler second light mission was born, which is a two-wheel mission that uses the solar radiation pressure to stabilize the telescope, as you can see on the figure on the left. This means the telescope is pointed along the ecliptic, which also limits the duration of the observational campaigns before the spacecraft needs to be reorientated, which is why K2 is structured in these campaigns. One of which, campaign 9, was a dedicated microlensing study towards the galactic center, where approximately 3.7 square degree field is observed with a long 30-minute cadence. This is formally referred to as the super stamp and is predicted to exhibit a large number of microlensing events in free-floating planets, hopefully. So the campaign ran between the 27th of April 2016 and the 1st of July 2016. The aim of the whole campaign was to simultaneously observe gravitational microlensing events from K2 and from Earth with ground-based telescopes in order to see a parallax affecting the shape and time of the lensing event. This data was first blindly searched by McDonald et al. 2021, who presented their pipeline. So they they get calibrated images from MAST, which they then use the Plesk et al. 2019 MCPM model to extract light curves, which are passed through this pipeline of progressive cuts, which are detailed on the figure on the right. But so their data reduction process is guided by this complexity of the data, which I'll get to in a second. And they use an ad hoc approach of combining pre-filtering and pre-whitening of the data together with a generalized analysis to detect peaks in the light curves on K2C9. Notably, Kepler was built and optimized for a transit study towards the Cygnus-Lyra region. However, in this crowded field towards the galactic bulge of K2C9, Kepler's large, approximately 4 arcsecond pixel size leads to, as well as the loss of two of its reaction wheels, lead to complexities in the data, such as an undersampled stellar point spread function, as well as drifting across detector pixels of light. And it is challenging to reduce the data with standard photometric pipelines. So to address all of these challenges, Plesk et al. 2019 present the Modified Casual Pixel Model, MCPM for short, which is a new method to extract K2 photometry in these stellar, very dense stellar regions. I guess for completeness, I will briefly mention that MCPM mitigates this systematic variability introduced by the Kepler drift by identifying correlated patterns in the pixels surrounding a target object. It then leverages these correlations to remove noise from the microlensing signal of a target, assuming that the target is confined to a pixel centered on that source. So this is something that doesn't have to be done normally. It is specific to the K2C9 data because of these challenges. And I sort of mention it here qualitatively, but a full description can be found in the original paper in Astronomy and Astrophysics. And back to the pipeline, McDonald et al. Report on 5 new microlensing candidates, together with 22 additional events that had previously been catalogued by the ground-based surveys. 4 of these, the top 4, are very short duration events of effective timescales less than 0.1 day, which are consistent with an Earth mass free floating planet. And then the 5th one was a caustic crossing binary event, which was then modeled by a companion study by Specht et al. 2022 and reported as the first bound microlensing exoplanet discovery from space. And with all of that background, what we aim to do is automate this selection pipeline and verify this automated selection of free floating planets. And then under stage 2, build a simulation framework of microlensing events, inject these into a subset of the K2C9 data to get new catalogs, where each catalog has a subset of our simulated events to be passed through the modified selection pipeline, hopefully recovering the efficiency of Kepler by comparing the simulated events that passed through versus the ones that we injected. So what we mean by automating the pipeline is replacing this at the very final stages of rejection in McDonald et al. Are these visual inspections of the light curves that pass all of the automated cuts detailed in that flow diagram of cuts. So to manually reject sporadic noise or poorly fit stellar flares, periodic variables, and instrumental artifacts that might have passed these automated cuts, they employ this visual inspection. Because we want a fully automated pipeline, we instead choose to fit pixel lensing regime models to these light curves. So this was first detailed by Gold in 1996, the study of pixel lensing, and it describes microlensing in high stellar surface density regions, which are the usual target of a microlensing planetary survey. And in these regions, the sources of the events are no longer necessarily resolved objects. So in the semi-classical regime, the photon noise is dominated by the light from stars that are not being cleansed. And we choose to fit these models, assuming that each type of anomaly will have characteristic effects and on the light curve, and to help diagnose their impact, we calculate the median scatter differences in these 2 regions. So firstly, we compare the peak region versus the baseline region, and we compare the light curve and the model fit either side of the peak within a 10-day window for all of the surviving light curves. So an example of what a good fit or what an event that might pass as a candidate looks like is the one presented in the light curve there on the bottom right. So because the pixel lensing regime model is designed to fit a smooth symmetric light curve, characteristic of a microlensing event, at least in the simple assumptions, If the model is fitting well, it should accurately capture that smooth parabolic like rise and fall of the event, and then the baseline should be represented by the model as well. And as we can see by the values of the median scatter difference here, which are quite close to zero, this would pass as a microlensing event candidate. And this is actually one of the final candidates of McDonald et al. In the paper from 2021. On the other hand, light curves which might be events which might be rejected due to the fit are presented here. For example, the one on the left, where although it seems to be quite relatively symmetric, the in-peak versus baseline median scatter difference is quite high. This is something that we would characterize as a flare, and then or a rejection would also be triggered by fits like the one on the right, which is both asymmetric and it's a poor fit in general. This can be visually identified as a variable, but the idea is to remove this visual identification, which a rejection will be triggered by fitting our model as well. And then, just in terms of completeness, I will mention our second stage of the project, which is recovering Kepler's efficiency. So we have this framework of simulating light curves for microlensing events based on the mu-lens model of Pilecki and Yi of 2019, which we use to simulate a catalog with a subset of simulated light curves. We choose to do that for a range of masses from sub-Earth to Jupiter mass. In terms of the current progress, the pipeline seems to recover approximately 0.1% of the injected simulated events for an Earth mass free-floating planet. Final estimates are a few weeks away, so all of this is preliminary, but it looks like it'll be interesting to see what it looks like across the whole free-floating planet mass regimes. And just to summarize, the next steps are to finalize this pixel lensing regime fitting to all of the K2C9 data that passed the automated selection, the automated cuts, to produce a final selection candidates of free-floating planets. We will use this then to compare to the recovery efficiency of Kepler, which we still need to derive the theoretical detection rate of the free-floating planets in the galaxy. But as we complete analysis of all of the simulated microlensing catalogs, eventually we will compare the theoretical detection rates to the actual set of free-floating planet candidates that are identified and hopefully evaluate the galactic abundance of free-floating planets. Thank you.
Questions?
Thank you for the talk. I was curious if you understand the preliminary results, why the detection rate for terrestrial mass planets is relatively low. Is it based on the cadence or just signals that's limiting for recovery?
I think we expect it to be quite low in general. I think the data is noisy, and I think given that we only detected 5, given the McDonald et al. Report only 5, we were always expecting a low recovery. It doesn't seem that low to me. To be honest, I think the actual rate is a little bit higher. As we adjust our simulation pipeline, it will prove that the recovery is a little bit higher than that. But the data is not ideal, right? The Kepler survey was not ideal for this type of search.